So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now. Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another physics lecture. Today we are going to start our discussion on section 2.2, that is thermal properties and temperature. So the first thing in this section is thermal expansion. Thermal expansion states that it is a property of most metals and some other materials that when they are provided with heat, they expand. How do they expand? Basically, their molecules start to move or vibrate faster and faster, which causes them to knock into each other and push each other apart. Hence the distance between the molecules increase, though very slightly, but because of that the overall size or length of an object increases slightly. When this happens, it is the space taken up by the molecules that increases. The molecules themselves remain the same size. You need to remember this. Thermal expansion occurs in solids, liquids and gases. Means it basically occurs in all three states of matter. When temperature is increased at constant temperature, a solid will tend to expand the least. Gases will expand the most, whereas a liquid expands somewhere in between. The uses and consequences of thermal expansion. Thermal expansion of materials can have some useful applications, but there can also be some undesirable consequences. The application can be thermostats rely on expansion of liquids to measure temperature. Thermometers, not thermostats. In a thermometer, what happens, there is a liquid, mostly mercury, and when heat is provided, that mercury or that liquid expands and rises up in the column. Hence we get to know what is the temperature. Temperature activated switches work with a bimetallic strip consisting of two metals that expand at different rates. When heat is provided to that bimetallic strip, it bends by a predictable amount at a given temperature, completing a circuit, and whatever turning on a switch, and whatever circuit is connected with that switch, it turns on. Consequences: the expansion of solid materials can cause them to buckle. For example, metal railway tracks can be damaged, road surfaces can be cracked, and bridges can be damaged. Things that are prone to buckling in this way have gaps built in. This creates a space for the expansion to happen in summer season without causing damage. Now there's something that you need to know, that is known as scaling a mercury in glass thermometer. This is basically an experiment, and it would often come in P2 or P4 even. So you need to know how you can scale an unmarked thermometer. First, an unmarked thermometer is placed in ice. The reading of mercury, whatever is the level of mercury at that time in that ice, is marked at 0 degrees centigrade, because we all know ice melts at 0 degrees centigrade. Then the thermometer is taken out of ice. It is let to come to room temperature, and then it is put in boiling water. As we all know, the temperature at which water boils is supposed to be exactly 100 degrees centigrade. Hence, that second, obviously when the heat is provided to mercury, it rises up in the column, it expands, and a new reading is acquired. That new level of mercury in the thermometer is marked at as 100 degrees Celsius. The length between the two marks is then equally divided into 100 divisions. Why? Because the ice point was at 0 degrees and the boiling point is at 100 degrees. So in between, the length in between is divided into 100 equal parts to count for 1 degree each. The thermometer now has a linear scale. In other words, it has been calibrated or graduated. Now there's another thing that you need to know, is that is the specific heat capacity. When talking about thermal physics, you are often going to hear this word in your past paper questions as well. You'll either be needed to calculate SHC or specific heat capacity, or you'll be provided this value and you'll be asked to measure the temperature change, calculate the temperature change or calculate the energy change. When a body is heated, its associated atoms or molecules start to move faster. On a microscopic level, heat energy is stored in form of kinetic energy of molecules. The kinetic energy of atoms is described as a random thermal energy. When the sum of kinetic energies in particle increases, thermal energy also increases, because they are one of the same according to law of conservation of energy. Basically, the internal thermal energy is equivalent to the kinetic energy of moving particles. Hence, when kinetic energy increases, in other words, we can also say the thermal or the internal energy also increases, and temperature being a gross measure, and in this context we say that temperature is basically a measure of state of the what you can say, temperature is basically a gross measure of the internal energy or the thermal energy of a body, and when the kinetic energy of a body increases, its temperature also increases, or when the thermal energy increases, its temperature also increases. To increase the internal energy of an object by a certain amount, the amount of heat energy needed to be supplied depends on its type of material, rise in temperature and mass. This is known as or you can say the capacity of an object to absorb or release heat energy varies from substance to substance. It depends upon what type of material the object is made from. A specific heat capacity, that is denoted by a small c, of a body is defined as the amount of heat, that is denoted by Q, capital Q, required to raise the temperature, that is denoted by theta. This symbol is known as theta, by 1 degree of a unit mass by 1 degree, without going through a change in state. Basically, specific heat capacity means the amount of energy that is required to raise the temperature of, or let's suppose 1 unit of an object, let's suppose 1 kilogram of an object by 1 degrees. So the amount of energy that you provide 1 kg of water so that its temperature would increase by exact 1 degree centigrade, or it would be known as the specific heat capacity of water. Similarly, if you are heating an iron bar, then the amount of energy, whatever is the mass of that iron bar, let's suppose it is of 2 kg. So the amount of energy that you will be needing to supply to that bar through a stove or a burner, that would cause that iron bar to have an increase in temperature of exactly 1 degree, would be known as the specific heat capacity of iron. And obviously the specific heat capacity of iron and water would be different. For every material it is different. When the mass of an object is greater, the object will contain more atoms or molecules. Hence, when the temperature of object are raised, the more massive object will require a larger thermal energy. So in other words, an object with greater mass will have greater specific heat capacity. SI unit of not greater specific heat capacity, it would just require more energy. The Q would be greater for an object of greater mass. So Q and mass are directly proportional. Specific heat capacity for a material is usually constant. Like for iron it would be constant, just like density is constant for different materials. SI unit of a specific heat capacity is joule per kilogram per Kelvin or joule per kilogram per degree Celsius. So you can either be given the temperature reading in Kelvin or in Celsius. Both scales work fine. So the unit is written as J divided by kg divided by C, or J slash kg slash C, or we simplify things and write them in inverse form, J kg inverse and centigrade inverse, or J kg inverse and degree centigrade inverse. So the formula comes out to be Q equals to mc delta theta or delta T. Some students or some books denote it as delta T as well, but it is the same thing. C over here is the specific heat capacity, M is the mass of substance in kg, Q is the heat or thermal energy absorbed or released, and delta theta is the change in temperature, either in absolute temperature, means in Kelvin, or in degree Celsius. Specific heat capacity of gas is usually higher than the specific heat capacity of liquids, and much higher than that of solids. So a gas would have the greatest specific heat capacity, then comes the liquids, and then comes the solids. The substance with higher specific heat capacity cools or warms very slowly, as they need to acquire or release larger amounts of energy as compared to a substance with a lower specific heat capacity. With gases, the molar heat capacity, or the heat capacity of 1 mole of gas at constant temperature, constant pressure or volume, is generally more useful than the specific heat capacity, which is based on mass, as when we are discussing gases, we usually depend upon their volume and pressure and not their mass. So there's this experiment in your syllabus that says investigating specific heat capacity, how you can calculate or find out about the specific heat capacity. Now in this experiment we have to determine this SEH of a substance by linking the decrease of one energy store, or you can say or by the work done by an energy store or an energy source to increase in temperature and subsequent increase in the thermal energy stored. For this we note the following values: the time, the temperature or theta, then the material of the block, the current supplied, the voltage supplied, the potential difference. So what we do is we start by assembling the apparatus, placing heater into the top of the block, Measure the initial temperature of aluminum block from the thermometer. Turn on the power supply and start the stopwatch. When the power supply is on, the heater will heat up the block. Take several periodic measurements, for example every 1 minute, of voltage and current from the voltmeter and ammeter, calculating an average for each at the end of the experiment. Switch off the power supply, stop the stopwatch and leave the apparatus for about a minute. The temperature will still rise before it cools. Monitor the thermometer and record the final temperature reached for the block. The thermal energy supplied to the block can be calculated using the equation E equals to current I into V into time. T means current into volt into time, or you can simply use energy transferred in joules equals to power of heater multiplied by the time heater was on. The above experiment can be repeated with a beaker of liquid to find a specific heat capacity of a liquid. Now, how do we evaluate this experiment? In this experiment, we can have both systematic and random errors. Systematic errors can be that the voltmeter and ammeter are initially set to 0 to avoid any zero error. Random errors can be that not all heat energy will be transferred to the block, some will be lost to the surrounding. This means that the measured value of SCH is likely to be higher than the actual value. To reduce this effect, make sure the block is fully insulated so that no energy is lost to the surrounding. Often the examiner asks that what you can do to improve this experiment. So when the experiment is related to SHC or heat transfer, make sure that your first priority should be insulate the experiment or insulate the beaker of liquid or insulate the block of whatever material is given. A joule meter could be used to calculate energy directly instead of using voltmeter and ammeter. This would eliminate errors from voltmeter, ammeter and the stopwatch. Make sure that the temperature value is read at eye level to avoid parallax error. The experiment can also be repeated with a beaker of water of equal mass. The water should heat up slower than the aluminum block. Safety consideration: make sure never to touch the heater while it is on, otherwise you can burn your hand. Run any burns immediately under cold running water for at least 5 minutes. Allow time for all the equipment to cool before packing away the equipment. Keep water away from all electrical equipments. Wear eye protection if using a beaker of hot water. Sometimes the examiner do ask for safety precautions for like 1 mark, so you can write any one of these in that question. So this is an experiment to find a specific heat capacity. Now moving on, as we have already discussed, we have two fixed points of water. Ice melts at 0 degree centigrade and pure water boils at 100 degree centigrades. These are accepted values for pure water at atmospheric pressure. When a substance is changing state, either melting or freezing, or a substance is boiling or condensing, the substance does not change the temperature. This we have discussed while discussing the heating and cooling curve as well. Because energy is being transferred to or away from the thermal energy store of the substance. The thermal energy store of substance means its molecules and its atoms. That is why a temperature change do not occur. When liquid water is heated, temperature of the water rises until the water boils. At the boiling point, even if more thermal energy is added, the liquid water does not get any hotter. Because the internal energy is not rising, the energy being provided in form of heat is used to overcome the intermolecular forces between water molecules, and they are being liberated as steam. This evaporation or vaporization causes the water to become a gas, and this process is repeated backwards for cooling as energy is gathered. Energy is transferred in order to reform the bonds between the molecules, so the water droplets can be formed, so the water molecules can come together and the steam can form liquid water. This is known as condensation. A gas turns back into liquid through condensation. When solid water means ice is heated, then the ice melts, and at that point, unless and until all the ice has melted, the temperature does not rise, because the energy provided is being used to break the intermolecular forces between ice molecules or molecules of the solid ice. As these forces are overcome, the solid water becomes liquid. As these forces are eased up, as these forces becomes weak, molecules are liberated. This is known as melting. The ice is now a liquid. And this process is repeated backwards. When you put water in a freezer, then energy is being taken away from the water molecules until they stop moving. They come closer together, energy is released from them, and they form the bonds again and come together and solidify in form of ice. Now, one thing you need to remember is that at 4 degrees centigrade, when if you put water into a freezer at 4 degrees centigrade or till 4 degrees centigrade, water contracts. At 4 degrees centigrade until 0 degrees centigrade, it expands. This is an anomalous behavior of water. Below 4 degrees centigrade, water expands. After turning ice, water expands. That is why ice is able to float on top of water, and ice is less dense than water, because when water turns into ice, it expands in the last 3 to 4 degrees. This process is known as freezing. Evaporation is the process in which liquid change into vapor without boiling. It can occur at any and every temperature. In liquid, the speed of molecules in random motion are different and keeps changing due to the intermolecular bombardment, means intermolecular collisions. When a molecule near the surface of the liquid gets sufficient speed or energy, it escapes from the liquid surface and leaves behind a liquid with a lower energy or lower temperature. Evaporation could occur at any temperature. Basically what happens, different molecules, random molecules of a liquid take energy from their surrounding liquid and use that energy to propel themselves as steam away from the liquid. Since they take the energy away from their surrounding liquid, the temperature of the liquid decreases. At higher temperature, the process speeds up, like on a sunny day, clothes dry faster. Evaporation, rate of evaporation increases with rise in temperature and rise in the surface area of exposed surface. It also depends on the speed of wind, as wind or air plays a huge role in liberating water molecules from liquid water. And decrease with humidity of the atmosphere, pressure and boiling point of the liquid. At home, wet clothes are dried by evaporation. The water in the clothes is unlikely to reach its boiling point even though the clothes are hung under the hot sun. The drying of clothes is only done by evaporation. So boiling versus evaporation, there are some key differences. Substance changes its states in boiling, whereas in evaporation it changes its state without reaching 100 degrees centigrade. Boiling is fast, whereas evaporation is slow. In boiling, bubbles are formed. In evaporation, no bubbles are formed. Boiling occurs throughout the liquid, whereas evaporation only occurs in exposed surfaces of the liquid, or only at the top surface, top layer. Boiling occurs at definite temperature, that is the boiling point at 100 degrees Celsius or whatever is the boiling point for a certain liquid, whereas evaporation can occur at any and every temperature. For boiling, we need a source of energy. For evaporation, energy supplied by the surrounding, by the sun or by any other surrounding source. Now, so we'll keep it till here.
and we'll continue on with the rest of the section 2.2 in our next video. So stay tuned, take care. If you have any questions or problems, please do comment. Take care. Allah Hafiz.